And the next speaker is Professor Mikko Möttönen. So Mikko is the professor on quantum technology, and this professorship is rather new. It started 1st of April and was built up together between VTT and Aalto University. Welcome, and let's get into the quantum physics.
Thanks, Jussi, and I couldn't be more excited about this new announcement from Antti that we should build the Finnish quantum strategy. So I think we are living very exciting times here, even in Finland. Can you? How do I put on my here? Okay. So here's my first slide. Sorry. I have been introduced, so I don't have to say much. You just see the logos here, Aalto VTT. QCD Labs is my research group here. I can see some people from there here. And QTF is the Center for Quantum, Center of Excellence for Quantum Technology. I will talk about that a few words later. So what is quantum technology? And now I'm talking about the quantum technology 2.0. It's the new sort of quantum technology that we are talking about mostly here. That I define that we have systems or processes that we can control at the level of individual quantum states. So it's not like that you have only quantum effects in a macroscopic scale, but you actually can access the individual energy levels in a controllable way in your system and use them for some technological application. And now, by the way, who doesn't have a PhD in quantum physics? Okay. About half of the people. So I will talk about these individual energy levels later on. So don't worry. And I'll also try to talk in a way that you understand. So sorry about the guys who have PhD in quantum physics, but maybe you have some food for thought also from this non-math including talk. Okay, and so for technological applications, and if the application is computational problems, then we call this device a quantum computer. So this is a little bit extended definition, but I don't want to fight over names or terms here. But I think this is a fair definition of a quantum processor. Or I put here processor. Also, some people don't like the word computer that much because they think computer is something full, like with a screen and everything, and a processor is the chip that is making the computations. Okay. So what is quantum computing? I mean, now you basically know the definitions, but what is quantum computing? In a very simple terms, quantum computing is something that you have a problem, you feed it into the quantum processor. It may be this kind of a superconducting chip, for example, here. And then this chip uses these individual quantum levels, these individual quantum energy states, to do computation to solve the problem, and then you get the output. This is in a very simple terms. So it's basically like, you use it as like a classical computer. Also in a classical computer, you type something in, that's a computational problem. For the computer, it processes it, and then it gives the result. So for the user, it's not that much different. Of course, the way you type in the problem to this chip here is different. But if you have this graphical user interface, for example, like in IBM Q, you can learn to use it quite quickly. And later on, people will use quantum computers, and they didn't even know about it. That's like in artificial intelligence, for example, like Antti said. And now that we have this quantum technology popping up, not only in computing, but also in sensors and other fields of technology, people start to ask, okay, how will it change the world, and when it's gonna be here? And these answers, or the answers to these questions, there is not a single right answer, right? Because now the technology is here, and it's not gonna come to an end. we're going to develop it and develop it for decades and decades to come. It's like with the classical computer. I mean, still we are building in the world better and better classical computers. It's hard to say how that's going to change the world in the future, right? Because it's still going to go on. Oh, wait, even if the Moore's law will, will at some point come to an end, it will still keep changing the world. And the same will happen with the quantum computer or the quantum technology. We will keep on developing it, and it will keep changing the world. It's not a single event like this. Okay, now we have something crazy like flying cars, but it will keep changing the world. Okay, so now I try to tell you a little bit about what is inside the quantum processor. The quantum bit, oh, now this is, by the way, this is PDF, right? Okay, so my animations don't work here. Should have known beforehand, but I'll try to do the animations with my hands or something. Okay, so a quantum bit is also called a qubit. And the single classical bit is basically here 2 states, 0 or 1. Okay, you know that. Okay, that's kind of, at least in the abstract way, you think it's only 0 or 1. But actually it's not. It's a continuum of energy states. So here the vertical axis is energy. So in a classical bit, you can basically have any energy here in between. You think about a transistor, for example. That would be a classical, or well, no, it's even easier. Think about like this pointer. This would be 0, that would be 1. Okay, if you want to change from 0 to 1, you gotta take the pointer down in energy. Or if you so you have all the states actually in between. But in your classical computer, you will just put a threshold here. Okay, so if it's above this level, you say it's 0. If it's below that level, it's 1. But actually, there's, you know, zillions of states between these two. But in a qubit, there is only 2 states, physically. Not only in the in your abstract computational math, but it's physically only 2 states. So this is the minimum amount of states, the physical states you can have to implement a bit, but then it becomes actually a qubit. And the reason is why it has different properties is exactly this quantization. We call the discrete amount of states quantization. This is the simplest case, 2 different states, so 2 discrete states. So, okay, don't worry about this slide. Okay, the animation would have gone so that, okay, we start from 0, and then this ball, this would mean that we are in the state 0. And then if you want to move to state 1, how would you do that if you can't go in between? Any suggestions? Answers? Risto, do you have any idea? How would you move from state 0 to 1 if you can't move in between? Well, that's a good answer, but then we have to bear in mind that you know, the reality, the physics, that's continuous. There is no real jumps. I mean, that's how we basically observe that. It's continuous in time. In the quantum world, if you think about the time evolution, it's also continuous, so there's no real jumps. If you would have a real jump, that would be like a singularity in energy. So the only way, what if you're between the jump? So make the jump continuous. So basically what happens is that this starts to disappear from here and starts to appear from here. That's the way the transition happens in the quantum world. It can look to an outside observer instantaneous jump, but in fact, that's the way it goes. It starts to disappear from here and appear to here. So it's a very different way of the classical bit of moving up and down. So this comes only from the two assumptions. We have quantization and continuous evolution. And there you have the superposition. in between this transition, the system is or has to be in these two states at the same time. And that's the superposition. So now, I hope even the guys and gals who didn't have a PhD in quantum physics kind of have a little bit of an understanding why this superposition happens. And it really means that it's at the same time in these two states. And one of the funny things here is that actually if you try to drive the system from state 0 to 1, and you keep on driving, so it disappears from here, appears to here, and if you keep on doing it, it can't go. I mean, it can't go anywhere else except back to 0. So in fact, it starts to oscillate between 0 and 1. Instead of the classical system, if you push it further down, it just goes down, because there are states further down. But in a quantum world, that's not going to happen. And these are the properties of quantum bits. They are very different from classical bits. These are the fundamental properties. And actually, what turns out is that it's not only the probability, like there's some probability being here, some probability being here, but there's an additional degree of freedom called, and we call it a quantum phase. And this quantum phase is very important to actually get these quantum speedups. Without that, there would be no speedups. So let's look at the single qubit in a little bit different way. So again, we have the 0 state and the 1 state. And then you can describe all of these superposition states with this sphere. So every point on the sphere, it doesn't mean that the eigen, or if you measure the energy, that the energy would be something in between. But now these points just mean that this means that how much probability there is being in 0. I mean, it's basically this angle here. This is fully 0, this is fully 1. And then you have another angle that describes you the so-called quantum phase, which is a little bit harder to understand. But anyways, there are these two variables in a single qubit. So imagine that you would encode the qubit to a classical computer. Well, that's very easy. I mean, if you use double precision floating point numbers, you need 16 bytes, for example, to store these two variables. That's a piece of cake. To calculate a single qubit quantum processor, all the dynamics in a usual computer. Okay, so what is that? What is the advantage, or what is the difficulty then in quantum computers or simulating those? Okay, let's imagine 2 qubits. I don't know anymore how to draw this simple sphere for 2 qubits. Instead, I now write it as this kind of sum of all the different states, the basis states. These are the energy states, the discrete states. And then you have these coefficients here. And now actually these coefficients here tell you what the state is. If everything else is 0 and this is 1, then you are in the state 0, 0. But during the computation, these coefficients can take almost any values. So in effect, there are 6 variables here. These are complex numbers, but you take 2 variables out because the probabilities have to sum to 1, and the global phase doesn't really matter. So that means 48 bytes. That's also a piece of cake, you know. Any computer has that many bytes, or it's not gonna do anything, right? Okay, but let's take 1,000 qubits. That's these many variables, 10 to 300, and that's just an insane number of bytes. Just, you know, forget about it. Even if we wait for thousands of years for Moore's law to take place, you wouldn't have capability of calculating that, or actually the physics would hit the fan first, because there are less than 10 to 100 particles in the visible universe. I think it's like 10 to 70 or something. So even if you would encode a single byte to every particle in the universe, you couldn't simulate with a classical computer, the quantum computer with 1,000 qubits fully. So this shows you that it's impossible to use classical computer to fully simulate a quantum computer, but it doesn't really tell you that quantum computer can do something better or faster than a classical computer. It tells you that quantum computer certainly does something that a classical computer can't do, but is that useful? That's where the quantum algorithms kick in. So you really have to be, then you have to have the PhD in quantum physics, I would say, and how to design the computer to work such that you solve some real-world problems efficiently using these degrees of freedom. Okay, so let's take like an abstract view. In here, I was saying that you have so many variables, and you know this was a 3D case with 2 qubits. So with many qubits, it's a very multi-dimensional computational space. So let me shrink all those multi-dimensions into the 3D sphere. So basically or the ball. So basically the surface of the ball and the interior now would be the quantum world. That's the multi-dimensional space. This is just a thought experiment or like a visualization of that. And let's say that the classical world is a lower dimension, has a lower dimension. So the classical world would be this arc on the sphere. And what is quantum speedup? Well, now you see that if you take the classical solution, if this would be your input and this would be your output, you have to go around, you know, the equator. In a quantum world, if you have a quantum computer, you could dive into the sphere. You could do this kind of a path in the sphere, but that's a longer path. There's no speed up. But if you want speed up, you will take optimally the shortest route. So then you have quantum speed up. So basically you take less steps to achieve the output from the input. No. Only this is on the surface. This goes inside and that goes inside. Sorry, it's a very...
Is it an, I would say, hollow ball or a fully filled up ball?
Ball is a field thing, and a sphere is just a surface. That's how the mathematics called it. So the quantum world is the surface. Quantum world includes the classical world. And quantum world is the whole surface and the interior of the ball. That was the quantum world in this example. So this means that if you live in the quantum world, if you have a quantum computer, then you can dive into the ball and take a shorter path. Is it now clear?
Okay.
Still not clear. Huh. Who knows what is in the middle? Okay, that's a socio-economic question. Who knows? Okay.
That's actually a good example because there are some problems where you don't get a speed up because you can compute them classically at the same speed as in quantum. So the dots would be fairly close to each other. And then there are some problems where the result or output would be completely at the other side of the sphere.
Right.
The saving would be much bigger.
Right.
It's actually a good way to explain.
Yeah, well, this is the simplest way that I could thought of. But thanks for this additional food for thought. Okay, but now let's think: is quantum speedup necessary for quantum computers to be useful? Well, now my animations again don't work, so you have to answer here. It's actually not even necessary for the quantum computers to calculate something faster than a classical computer for them to be useful, because it can be cheaper. Let's say that, okay, for some reason we could build very cheaply quantum computers. Maybe IBM doesn't agree, but maybe someday. Or it could be more accurate. So if you are used to the fact that classical computers are exact, they don't make any errors, right? But there are some problems that you solve with classical computers, but you have to make approximations to some, for example, quantum chemistry simulations. But what if the quantum computer would give you a more accurate answer, so you trust it more? You don't need so many approximations. So that would be useful also. So this is called quantum advantage. If you have faster, cheaper, or more accurate solutions from a quantum computer, then they become useful. So far, we don't know, or well, we don't know of any quantum computer giving quantum advantage. But we hope to see those very soon. Okay, so now I have about 8 minutes. I want to tell you a little bit about the, I told you about the qubit, and now I want to tell you about what happens inside, the processor, what you need to do to actually run the processor. So, okay, first you have to start with qubits. So you have to have some sort of physical system that has these controllable two states. That you can, first of all, you can initialize the state, for example, to the 0, that's the blue ball here, and then you can transition between these two states. You can basically do these rotations of the arrow on the sphere. Those are called quantum gates or quantum logic. And then you have to be able to read it out. So you have to be able to read out whether it's 0 or 1. That's very simple. That's exactly the same conditions than in a classical computer, right? You gotta be able to flush your memory, process the information, and read it out. But now you do it with these qubits, where the quantum gates are, the logical operations are very different. And here I have a picture of a superconducting circuit. It's this, the qubit is the X here. And the reason why we are mostly focused on superconducting qubits here is that they have been improving a lot during the years. So actually last week it was the 20th anniversary of the superconducting qubit, and some people, who was actually in this, was there anybody? Oh yeah, you were. Oh yeah, Jan was there in the anniversary seminar that was in Japan. But 20 years ago, the superconducting qubits, you can see here on the y-axis, you can see the lifetime of quantum information in the qubit. So 20 years ago, the quantum information was very short-lived. So it got destroyed almost immediately once you created it, like in a nanosecond. But now along the years, there have been very many improvements. And now we are in a place where we think that we don't actually need to improve the lifetime anymore so much that the quantum computer can become useful. And why this lifetime is important, of course, is that your quantum gates, or the readout, when you do those, of course, you don't want to have errors in these operations. And if the quantum information is degrading while you are doing the operation, then you will get errors, right? And the reason, again, why these qubits are so sensitive is that you only have these two states. So, so any perturbation on the system is going to be reflected in the state of the system. In a classical bit, if you wiggle it a little bit like this, okay, it's still below above the threshold, doesn't matter. But for a quantum bit, it's just the two states. So take a little bit from here and put here, it does matter. So you want this lifetime to be very long. And it's long enough so that you can actually run multi-qubit algorithms. For example, Antti talked about the IBM Q. That's online, and you can use it, and you can run it. And then, but the way to really go to the fault-tolerant quantum computer, which would then not make errors, actually is to use quantum error correction. So you gotta encode your quantum information into more physical elements. So you use many physical qubits to implement a logical qubit. That's understandable, because also as I said, in the classical computer you have all of these different states, and that's why they are so error tolerant. Now you have to little bit sacrifice. You use many states to present the logical qubit, and then it's possible, at least theoretically it's been shown, and also preliminary experiments have been made to show that this kind of thing works. That when you increase the size of your logical qubit in terms of physical elements, the logical error is shrinking. So this is, the next or one of the next big steps to show that this fully works in a quantum processor. Okay. Here I will just have two references to tell you what is the state of the art. So this partial quantum error correction has been demonstrated in a linear chain, not in this 2D array that I was talking about in this work. So they show that the bit flip error, so not the phase flip, but the bit flip, this error, that the qubit flips from 0 to 1, that error decreases when you increase the size of the logical qubit. And then there is the IBM quantum computer, the 20-qubit quantum computer, where IBM has shown that you can actually do a 2D lattice of these qubits. So now, if you would put these two together, and everything would work very nicely, at least as nicely as here, then you could demonstrate the single logical qubit. So that is more or less the state of the art now. There are, of course, announcements that there are 50-qubit processors, 72-qubit processor, 120-qubit processor, but so far I have not seen any scientific evidence that they work on that scale, the 50-qubit scale or 72-qubit scale.
Is the error correction calculated like the normal error correcting code?
On the high level, the principle is the same, but the details are different. How it works is that you measure the error. You don't measure the state of the qubits, but you measure whether these bit flips happened, and then you can account for that in the future computations. But the basic principle is the same, that you basically have the information encoded in many qubits, and then you can measure with some ancillary qubits that whether these qubits are in the same state or different state. Okay, so there are already some companies, IBM mentioned many times, but some other companies as well, who are working on the quantum computers. But I would also like to highlight the local center of quantum technology that I already mentioned on the first slide. So this is a very good example of what we have here in Finland. Not everything that we have in Finland, but a good example of that. And it's a center formed by Aalto University, VTT, and University of Turku. And I also know that in VTT there's also a strong additional effort in quantum technology. And in Aalto we also have a center for quantum engineering that is broader concept than this. And so there's lots of effort here in Finland. And now I think I put this to.
Yeah, it's time.
Yeah, I think I have 1 minute now. I put it to ring a little bit before. So I have 1 minute time to just say you that we have some nice, unique results that have come out from the local community. For example, we have a refrigerator that we could use to reset the qubits very quickly. We have done a new invention that we can measure the qubits more quickly and accurately, or it's a new way of measuring the qubits. And then there is a glimpse to a lab, actually to our lab, one floor down from here. You can see how it looks like. Actually, I think David will more show you pictures of this kind of cryostats that they are making here also in Finland. I'd like to thank my research group and all the collaborators and funders. And yeah, thank you for your attention.